Hello everyone, my name is Mohammad Nazibul Hasan. I'm a PhD candidate at Micro and Nanotechnology Research Group School of Electrical Engineering, Universiti Teknologi, Malaysia. First of all, I would like to thank the organizing committee of IEEE Symposium on Industrial Electronics and Application for giving me this great opportunity to present my research topic in this conference. Today, I will be presenting my topic on finite element analysis of thermoelectric power generation from human race on behalf of my other authors. The rest of this presentation is as follows. There will be a brief discussion about energy and the need of renewable energy technologies. The working mechanism will be discussed in the context of our proposed technology, and then our conceptual design will be presented. And finally, the results will be shared. As we know that energy is very essential in this world, and human needs energy to function all the essentials, including both indoor and outdoor applications. Many of us might be curious to know that how much energy our country uses. Well, according to US Annual Energy Report, even Malaysia is consuming 1.2 kilo terawatt hour energy, which is very high, which is a huge amount of energy. Now the question is, who exactly fulfill the growing energy consumption demand and from where all the energy comes from? Well, so far oil produced most of the energy, which is around 53.6 kilo terawatt hour energy, followed by the coal combustion. However, the oil and coal burning are escalating the concern about environmental degradation like air and water pollution, as well as the rise of global warming. Thus, all these issues have piqued researchers' interest in the development of efficient and renewable energy technologies. Renewable energy technologies have been developed to transform ambient energies such as solar radiation, heat, mechanical vibration, air or water movement into electrical power by means of renewable energy transducer, including solar, wind turbine, hydroelectric, as well as by a few other microscale transducers. These technologies, however, good for powering high power devices such as lighting, heating, cooling. Now, when it comes to powering low power devices, can these technologies be used? Well, due to the huge size of these technologies, it's very difficult to integrate with the devices like wearable sensors, ECG sensors, wristband. Moreover, these wearable devices needs a constant energy supplies to fulfill all their energy demands without having any power interruptions. Alternatively, piezoelectric generator, triboelectric nanogenerator, thermoelectric generator have shown as promising alternative that could significantly enhance the lifespan of the wearable and biomedical devices while maintaining a sustainable environment. These transducers can be utilized as an extension to battery to provide long-term power or even as a sole power supply. However, there are several disadvantages associated with these energy generators. For example, piezoelectric generator, most of the materials that are used to fabricate this generator are poisonous and brittle. Whereas in terms of triboelectric nanogenerator, the main disadvantage is the high aversion of the triboelectric materials due to the surface friction. However, thermoelectric generator provides the solution to all these problems. Now, why thermoelectric generators? Well, thermoelectric generator is a heat energy transducer. Since heat is one of the most widely used or accessible source of energy, which can also be produced by human body, thus thermoelectric generator holds an advantage for harvesting energy and powering especially the wearables and biomedical devices. Thermoelectric generator is a solid-state device which is used to convert heat into electrical energy by means of Siddique effect. It combines several pairs of thermal elements, which could either be any dissimilar metals or could be any p or n-type semiconductors. Now, let me show a tiny video to illustrate its working mechanism. As you can see in this video, when the heat source is applied on the hot side of the thermoelectric generator and the cold side is exposed to room temperature, a temperature gradient is formed across the thermal interface. Due to the movement of the majority of the charge carrier from a higher to lower concentration, which is produced by holes at the p-type and by electrons at n-type. Consequently, an open circuit electrical potential will be produced across these thermal element pair. Although thermoelectric generators have an edge in powering wearables and biomedical devices, nonetheless its output power is still very low. Thus, to enhance the output power, several studies were carried out while developing a highly efficient thermoelectric generator. It can be classified into three types, as can be seen in the figure. Firstly, various thermoelectric materials have been applied at different temperature levels. For instance, at near room temperature, bismuth telluride and lead telluride are the most efficient material and have been extensively used. However, lead telluride is a poisonous material due to the presence of lead. Thus, mostly bismuth telluride is used at near room temperature. In addition, several studies were carried out on segmented and cascaded design of thermoelectric generator. Well, it improves the output power to some extent. However, it requires very complex fabrication technique. Moreover, a few studies have investigated the enhancement of power with optimizing thermal elements like geometry. Most of this study reported on the analysis and numerical modeling of thermoelectric generator without showing the actual heat harvesting environment of the human risk. So, in this paper, the aim of this study was to design a three-dimensional thermoelectric generator module utilizing highest efficient NNP-type bismuth telluride materials and evaluate its power generation from human wrist using finite element analysis. The figure shows the conceptual design of our proposed thermoelectric generator to harvest heat from human body wrist. In this work, we employed 5 pairs of highly efficient NNP-type bismuth telluride material. All the equations that related to this work, such as voltage, maximum power, thermoelectric, power efficiency factor, is presented in this slide. These are the dimensions of the thermal elements as well as for the electrodes that we used in our model. These are the properties of the bismuth telluride materials that we have used to model the thermoelectric generator. We used COMSOL multiphysics to perform finite element analysis simulation for our proposed design. The simulation includes both heat transfer and electrical transport equations. And on the right side is you can see that assumption that we used during the simulation. The following section presents the simulation results and analysis of the proposed thermoelectric generator. The results of the simulations are present in this section. In this model, we consider the maximum temperature gradient that a human wrist can produce with regard to the environment. As figure shows that the temperature distribution through the thermal elements, when a hot side temperature of around 310 Kelvin is applied to the top of the thermal elements, just to develop the actual human wrist heat and to maintain a temperature gradient of around 12.5 Kelvin. From this, a voltage of around 8 millivolt was obtained for a single pair of thermocouple, and around 40 millivolt was produced by 5 pairs of thermal elements from human waste heat. The graph shows the enhancement of voltage with increasing number of thermal element pairs. As you can see from the graph that voltage enhanced linearly with the increased number of thermocouples from human waste heat. In terms of output power, with increasing number of thermocouple pairs, the power also enhanced. Based on the simulation, a maximum output power of 4.24 milliwatt was obtained for 5 pairs of thermocouples from the waste heat. And in terms of thermoelectric power efficiency, output a maximum thermoelectric power efficiency of around 67 microwatt per millimeter square per Kelvin square was obtained for 5 pairs of thermocouples from human waste heat. So, our aim of this study was to design a wearable thermoelectric generator for human waste heat harvesting. In this study, we also achieved an optimum temperature gradient for thermal elements varying the height and area of the thermal elements. As a conclusion, a voltage of 40.7 millivolt and output power of around 4.245 milliwatt and thermoelectric power efficiency of around 0.67 microwatt per millimeter square per Kelvin square was obtained for 5 pairs of thermocouples from human wrist heat. In the future, the use of conducting polymer can be seen more in wearable thermoelectric generator fabrication. This concludes our presentation. Thank you for your kind attention.